So the last talk tonight will be Marco Bernardi, and he's a professor of applied physics, and materials science at Caltech. He developed methods to investigate electron transport, ultrafast electronics, and light matter interactions. The title of his talk is Quantum Interactions in Materials, a New Frontier in AI.
Okay, well, thank you, and I would like to thank the organizers for inviting me and all of you for being here. So as the last speaker of the evening, it's very nice to close, very day of wonderful talks, but I also understand my responsibility that I stand between us and dessert, and so I will try to make it short and sweet. Now, so today I'd like to share our work on understanding interactions in materials using computational methods. And in particular, I will emphasize a recent discovery that AI and machine learning methods can tremendously help in this research. So as you know, computation has emerged as a third pillar in science next to experiments and theory. We're lucky enough that we're able to use computers to solve intractable problems or simulate complex physical systems. And also, and this is particularly true for AI and machine learning methods, we can attack problems in completely novel ways. So this is true, as we've seen in today's talks, kind of across the board in science and engineering, and it's also true for materials. So I work on computational materials physics. And in particular, we focus on a set of techniques that are called first principles calculations, where the idea is the only input to this calculation is the structure of the material, so kind of like where the atoms are and what atoms you have. And then using only the equations of quantum mechanics solved on a computer, you try to make quantitatively accurate predictions of materials properties. So the workhorse in this field is density functional theory, which is basically a method to accurately predict the structure and bonding in materials. Walter Kahn won the Nobel Prize in chemistry for this method about 30 years ago. But now there's new generations of techniques that are building on top of that advance. And so in particular, we focus on studying interactions in materials using many-body theory techniques. A couple of examples that I will show today. One is the interactions between the electrons and the atomic vibration. And so a quantum of atomic vibrations in a material is called a phonon. So that's the electron-phonon interactions. The electron spin also interacts with the atomic vibrations or phonons. And we also calculate a much wider range of interactions between funny named things like excitons, magnons, polarons. My wife always laughs at these names. Now, once you have these interactions, you can predict a wide array of properties related to, for example, transport, spin physics, devices, non-equilibrium physics, and so on. And so our group is at the forefront of this effort. In particular, we developed an open source code that's widely used in the community and kind of shares these methods with the community. Now, what's the societal relevance of this work? Now, if you think of your cell phone or computers, like the materials that go in the chips, like silicon, we pretty much understand everything about these materials. However, the next generation of materials that we're going to find in devices are going to be dramatically more complex. For example, people are using complex transition metal oxides, like strontium titanate, to make transistors. Or they're developing devices that are based not on the electron's charge, but on the electron's spin to make spintronic devices. And also, using the electron spin, they're trying to build quantum computers. And then finally, we can conduct electricity without losses at relatively high temperatures by relying on interactions that pair electrons in high-temperature superconductors. So to understand this phenomena, you need hardcore quantum mechanics. And so as you enter, put it here, this quantum era of materials, we basically need new sets of computational tools. And in particular, understanding interactions is truly central to this effort. I will show you just one technical example here, because before I start talking about the AI portion of this work. So we said that the electrons interact with the atomic vibrations or phonons, and so these interactions can be computed using first principles techniques. In particular, if you have an electron in a certain state n with momentum k, it's going to scatter into a different electronic state by emitting or absorbing a quantum of atomic vibration or phonon that carries a certain momentum q. Typically, you need to compute these interactions on very dense grids, and so you end up with billions or trillions of these interactions in a calculation, and you could view them as very large matrices or high-dimensional matrices called tensors, okay? Now, once you compute them, the beauty of this is basically without using any input from experiments or any free parameters in the theory. As we have shown in this work, for example, you can predict the mobility in a semiconductor with a spectacular accuracy, and then with a similar accuracy within about 1% of experiment, predict the time scale for the mechanism that limits electronic transport in this material. If you extend this theory to spin, you can predict the time scale for an electron spin to flip in a material. That's essentially the main figure of merit for spin-based devices, and you can see here, this is a prediction of spin relaxation times in silicon that is highly accurate without any tuning parameter over a wide range of temperatures. So when we started doing this work, when I started at Caltech about 10 years ago, these calculations at the time were essentially impossible. We just didn't have the tools, didn't have the code. Now we're at the point that for simple systems, this is kind of standard, and you can push it to materials with maybe tens or about 100 atoms in the unit cell, so fairly complex systems. However, one aspect of this that has always made me uncomfortable is, as a physicist, if you look at this, you're basically using billions or trillions of parameters, so to speak, to compute a property. These parameters are not tuned, they're computed, but the question is this an inherent complexity of the problem, right? So with that idea in mind, with a student of mine, Yao Luo, we started thinking about whether methods borrowed from data science / AI machine learning could help us understand if there's an inherent complexity and how you could simplify it. In particular, we started considering a method that's called singular value decomposition. This is basically just diagonalizing a matrix, but for a rectangular matrix, okay? So you decompose your matrix M as a product of two unitaries and a diagonal matrix, where the diagonal entries are called singular values. These are real positive numbers. You can arrange them in descending order. The beauty of this is that when the singular values decay rapidly, if you keep just a few of them, you obtain a very faithful approximation of the matrix, because this basically encodes patterns in the matrix. You can apply this to an image. So if your matrix is an image where each entry encodes the gray level of a pixel, you can see how, when this method works, you can keep just about 1 to 5% of singular values, and you're still able to see what the image encodes. And so for this reason, these compression techniques are becoming quite broadly used across quantum science. In our case, we asked the question, can you blur quantum interactions in materials in a similar way as this image and still make reliable predictions? In this work, we have shown that, quite surprisingly, the answer is in the affirmative. You have to find the right way to compress. In particular, for the electron-phonon interactions, we learned that you have to represent them in a real space basis with localized orbitals. And you can also compress the short-range part, which is really the difficult one for which you need quantum mechanics. Once you do it, you know that it works because the singular values decay rapidly. And the beauty of this is that now, keeping only about 1 to 2% of singular values, you can predict any properties that depends on electron-phonon interactions with the same accuracy as the full calculation. Now, on one hand, conceptually, this reveals that there's a hidden lower dimensionality where now you slash the complexity down to about 20 parameters per atom. In practical terms, the cost of this algorithm is proportional to how many singular values you keep. So basically now we can do the same calculations 2 orders of magnitude faster without any loss of accuracy. And so we've been particularly intrigued by this, and obviously we started asking the question, can you do it for other types of interactions in matter? I will show you this example of interactions between phonons. Again, quanta of atomic vibrations, and the interactions between phonons essentially govern heat transport in most materials other than simple metals. Typically, the interaction between three phonons, which you could view as a function of three momenta, governs the thermal conductivity. However, if you have a material that has soft bonds, the 4-phonon interaction and 5-phonon and beyond can also be important, but these calculations are extremely difficult to do at present. So here, again, we borrowed ideas from AI, in particular, a method that's called CP, tensor decomposition, that generalizes singular value decomposition to functions of multiple variables. So now your interaction between n phonons is a function of n momenta, but you want to write it in a simpler form, a product of functions of single momentum, and you sum as many of them as needed. The way this is done is through a tensor learning algorithm where you basically match this postulated form and you learn the best possible values for this function to match the entire multivariable function. So this is a tensor algorithm with encoded in PyTorch and GPUs and so on. Now, once you do it, what we found that I think is absolutely remarkable is you can compress these interactions even more than you could with SVD. For example, here with this method that we're calling permanent CP, because we had to adapt it to interactions in momentum space, you can compress the phonon-phonon interactions by about a factor between 1,000 and 10,000. And similarly, with the same compression factor, you can compress the interactions between 4 phonons and beyond. Now, in practice, that translates to a speed up by a factor of 1,000 for calculations of thermal conductivity. And I'm showing it here for 5 different materials, including very complex ones with low symmetry. And so this is truly something. These methods can tremendously help. Now, as a scientist, you're always skeptical, obviously. So if you are referee number 2, for example, you could say, well, you haven't really shown us anything new, right? You can kind of do the same calculations just faster. And so in some cases, it's possible. However, I would like to close with an example where I'm going to show you that's certainly not the case in general. There's a very difficult problem is when interactions become strong, okay? Then you can no longer use perturbation theory, which is basically what we've been doing up until this slide. And in the language of many-body theory, when the interactions are strong, you have to sum, in principle, an infinite number of higher-order interactions, which Richard Feynman used to draw with his diagrams. They're called Feynman diagrams. So you basically have to potentially sum all Feynman diagrams up to any order. This is not possible in essentially any physical theory. And I'd like to show you what strong interaction means for the electron-phonon problem. Here, if you have an electron, like it's shown in this picture, that interacts strongly with the atomic lattice, it essentially deforms the lattice around it and becomes trapped. So that's called a polaron, an electron that moves around and carries the lattice distortion with it. What we have been able to develop is a method that essentially adds up all Feynman diagrams for the electron-phonon interactions. And so in this work, we've developed a Monte Carlo algorithm that moves around in the space of Feynman diagrams. In this space, the axes are the order of the diagram, the topology, the number of internal variables, and you sample them all. And this is possible because you have compression. In this particular algorithm, compressing the matrices gives you a speed up by 4 orders of magnitude. So if we can do this calculation in a week to a month, it would have taken you something like 10 to 50 years, which is obviously not possible. Once you do this, you can essentially provide a numerically exact solution to the polaron problem, which is a long-standing challenge in condensed matter physics. In particular, you can compute polaron energies as a function of momentum. You can peer inside the polaron and see how many phonons it carries with it in the phonon cloud, what type of phonons you have, but also for complex oxides like anatase that are known to have polaron effects. You see here, our collaborator has grown probably the cleanest sample of this material, has measured its transport properties, and this method can predict the polaron mobility with a remarkable accuracy. So that's something that if you didn't have these compression techniques, you would essentially not been able to do. Okay, so let me close here so we can resume our plan of eating dessert all together. So what I think that we have developed is essentially a new paradigm to study interactions in materials. You can speed up calculations, solve intractable problems, but also the future looks very promising because now obviously we're on a quest to compress a wider range of interactions using more sophisticated tensor learning methods, including some of the ones that Anima has developed. And then you can take it kind of a step beyond. For example, instead of compressing, you could think of learning interactions directly in compressed form, or another holy grail would be that, for example, starting from the crystal structure, you can directly predict the interactions bypassing any first principles calculations with a machine learning model, or form a library of interactions in materials and find patterns with data-driven methods. So I'm particularly excited, again, about this new angle on this problem, which is entirely enabled by AI and machine learning techniques. If you want to read more about this, besides the papers, Caltech has been nice enough to write 3 stories that kind of convey the general significance of this work. So yeah, thank you.
Thank you.